Hello. Hello. I don't do Teams. No. I mean, I'm not going to say that I'd rather die, but I mean that at CISPA we don't use Teams, and I'm very happy with this. Hello. Can you hear? Yes, it does work. Its interface is completely useless again. Yeah. Okay. Oops. Okay, I would slowly but surely like to get started. So if those who are still walking around can find a seat, do it quietly, then yeah, good. Right now, for the time being, it's still last week for a few more minutes. Then at one moment, be it right after in the intermission between this or last week and this week, we have a guest, Anna Maria, who has an announcement to make to all of you who are a master student. It's up to her to explain why she's not interested in bachelor students, right? But I'm not going to touch that. And then afterwards, I'm going to continue with the actual topic for today, support vector machines. So that's the rough program that we have planned. And maybe, depending on some technical issues, Anna Maria will show up a little bit later while I'm already talking about support vector machines. Good. So right now, it's, what day is it? It's again the 18th of January. And we're still talking about, well, we had just spoken about trees and we were talking about forests. I'm going to give you very quickly a recap. Not about trees, we still have this fresh in our mind, right? We just split the data, we get one tree. One of the problems that we saw is that decision trees and regression trees, that they're quite brittle. They have a very high variance. With a little change in the data, you're going to get a different tree. And no, they're also, because we grow them greedily, they can very easily fall into a pitfall where they choose, because of like slight differences in the data, they take a split like this rather than that. And because your data is now split into two parts, you can never really merge these parts again, right? So yeah, they're in a way a bit too greedy. One of the ways to fix this is to not use trees at all, but hey, what's the fun in that? The other way is to say, hey, why don't we learn multiple trees and combine them in a smart fashion? Well, the moment that you're combining multiple models that you've learned and you combine them in a smart fashion, then we call it an ensemble method. You tap into the wisdom of the crowd. So as long as each of the members of your ensemble is not a complete random coin flip, right? It has a slight bias towards the right answer. You actually will get, if you average out the decisions of each of these slightly biased or strongly positively biased coins, you get a much better classifier overall, just by taking a majority vote over each of these weak learners. If you think about doing this with trees, there are three main methods that we can use, two of which are already explained in Bird's Eye of Bird's Flight last week. I will do so again. And a third method that I will spend a little bit more time on today. The first is bagging. And bagging, you still remember, not just from last week, this week, but also from earlier. We just randomly sample endpoints, uniformly at random, but with replacement. And we have then a new data set of the same size as the original one. We do this multiple times. And for each of these data sets, we learn a tree. And well, if you now want to make a decision or you want to make a prediction for any wild new data point that appears, you just ask each of your trees, what is your output? We take it either by an average, that would be if it's a regression tree, or you take the majority vote if it's a classification decision. And all of a sudden, you have a slightly better learner. That's bagging. No magic there. One of the big problems with bagging is that you have a very high correlation between the individual data sets. So the chances that you get really different trees for the one bagged data set versus the other, it exists, but nah, it's not that great. In particular, this is a problem when you have some features that really dominate the splitting criterion. So these are features that look fantastic when you start splitting, only for you to later realize, oh shit, I actually shouldn't have done this. And as we also already just said, trees have no way of retracing. So rather than always looking at the entire feature space and just changing the data by randomly sampling, we can also randomly sample the feature space. And then we are what's called a random forest. So what we now do is we do not resample the data. We just always use the same training data, right? No problem there. But we randomly sample, in general, depends a bit on the task. For classification, square root of the number of predictors that we have. And for regression, roughly a third. In a way, much fewer than we normally have. And if you do this multiple times, then because square root as well as a third are much smaller than p itself, the expected overlap is not so great, and hence the correlation between the models that you have, and hence their decisions, is not, well, 100%, which you kind of have the risk with bagging. So that is the general idea of a random forest. And much more, there's not so much to say, except that random forests are some of the strongest classifiers available. In general, what you do with a random forest, you just learn, well, a reasonable tree. It doesn't have to be that deep. You don't have to learn it completely and then prune it back, because, well, if you learn enough of these random trees on random parts of the data, wisdom of the crowds kicks in. Now, it's better and very useful in practice and easy to learn. And I already gave an anecdote last week that you can also sell this as a, well, not deep learning, but you can deep trees, and it works almost as well as many finely tuned deep learning models, depending on application. But there is one other class of ensemble methods on trees that I want to discuss in slightly more detail, because they're slightly, well, more thought through, slightly smarter. Right? You could say that bagging and random forest, they make use of a nice trick, and it just works wonderfully well in practice. The method I want to discuss on the next slide, let's first look, okay, is there a difference? Very quickly. So single tree, that's the dotted line. The black line is bagging. As you can see for this particular data set, the error is slightly lower, not massively so, but slightly so. Then on test, this is what random forest does. So random forest has a much lower error, right? Just by drawing random feature spaces. Neither really overfit. So depending on how far you push it, of course, if with a random forest, at one moment, if you've seen all the possible parts, then yeah, well, adding even more so parts, I mean, slices of square root features, right? If you have used all of them, then adding more to your random forest is not going to make any difference. So you generally just grow a random forest of 10, 50, 100 randomly sampled feature sets. Okay. This I'm going to quickly skip over because I already gave you the intuition. You need a small set of features, not too small. If I only give you one feature, then you can't learn anything really, right? You're just doing univariate prediction. If I give you too many, well, then we have the same problem as with bagging. There's too much overlap. You always learn the same tree, so that is stupid. I'll get back to that in a second. Boosting is more interesting as a method for how can we now learn a bunch of trees, of forests, to, well, do a prediction task better than a single tree can do. The key idea in boosting is that it is stupid, what we're doing in bagging and random forest, to learn the trees all individually, independently. Right? In bagging, we sample a new data set, we learn a tree, we do it again, and we don't take in mind how good or bad the previous tree was. Same thing in random forest. We just sample some features, train a tree, and again, next time we have a bit of sort of Korsakoff type of short-term memory problem. In boosting, the idea is as follows. You learn a weak predictor, let's say a weak classifier. In terms of what is a weak classifier, what is a weak learner, something that essentially by itself does not stand a chance to do particularly well. Right? So something that is very far from being overfit. Overfitting is not necessarily a strong learner, right? But the key idea is just get a simple learner. In decision tree terms, what does this mean? A tree with very few splits. Sorry, Ben, I already gave the answer. It's with very few splits. In fact, even a decision stump, which is a tree with just one single split, often suffices. The only more stupid tree that you can think of is one without a split, and of course there you don't gain any information, right? But what we're now going to do is we're going to train a small, cute little tree, a slight bonsai tree, right? Maybe a decision stump. And what we're now going to do is we're going to see how good does this tree do? Where does it predict well, and where does it predict badly? And what we're next up going to do is we're now going to learn a new tree that tries to fix those errors. So we want a tree that does not predict the exact labels, because that's what the first tree was supposed to do. The second tree needs to fix the errors that the first tree makes. And the third tree is supposed to fix what the errors that the first two trees still leave, and so on and so forth. That is the general idea. So we're going to train decision trees sequentially, one at a time, each time trying to fix the mess that the others left, which makes sense, right, as an idea. That's the idea of boosting. Now, just look at the performance here. We again have a single tree. We have a random forest, that's the green line. I don't know why in the book the colors flip-flop all the time. That's not my doing. And then for boosting, with a tree of depth 1, so decision stump, respectively in blue, a tree of depth 2, you get these curves. And you can see that the decision stump, in the end, actually does better on test than the one where you have a slightly stronger tree. The deeper you grow your tree, the more expressed this most likely will be. In special cases, on your data, it may be that actually a decision tree with 3 splits is going to do best if you apply boosting. In general, don't bother, just the decision stump. The first algorithm in the name you should know, but we're not going to discuss it in full depth, is AdaBoost by Joa Freund and Robert Shapira. They got hundreds of thousands of citations on it and got very famous. The original version, I mean, they didn't have so much theory behind it, but in the 10, 20 years that followed, lots of people thought about what is now actually the idea, what can we prove about this? One thing stood for a very long time open, and boosting doesn't overfit, even though it kind of should in a way, but it doesn't. Well, this is a question that got answered in the last 5 years from different angles. So we now know why it doesn't overfit or when it doesn't overfit. For that, I would need at least 2 more lectures to properly introduce you to all the necessary techniques. So for now, boosting is just a magical technique that you should definitely use. The original AdaBoost is just for binary classification. I want to discuss with you a slightly more modern but greedy heuristic version of boosting that is sort of the building block for many other boosting algorithms. When I was saying earlier that, also that means last week, when I said, okay, random forest should be your go-to method if you want to predict something before you start training something that is very advanced. Boosting is your second tryout. Just see if it works. And if it doesn't, it might well be that there is nothing to predict in your data in the sense that the features you have are not sufficiently informative, right? So use these 2 methods wisely to see if there's actually any investment of time necessary. As you know, I hate showing pseudocode, but here we are, because the algorithm is very simple and actually walking you through it makes most sense to make you understand it. The initial model, model 0, is just a plain 0, right? This is f hat. And this means if we use f hat to predict it, well, the errors are going to be exactly what the output should have been, right? In that, so this means that the errors that this f hat made, these are the residuals. We can already call them residuals. This is for the first iteration. And now what we're going to do over multiple iterations from small b as 1 all the way to big B, and use as many steps as you feel comfortable in doing. Get to a little bit more detail there perhaps later. What we now do is we fit a new f hat. We're going to mark it with the small b to show that it's in which sequence, in which we allow d splits. And as I already gave away, setting d to 0 or to 1, such that you have 2 leaves, absolutely fine. Just do that. So you run it on the training data plus the residual. So what is the error that is being made? Now, the trick on top of what I just already gave you as the intuition is that we now update our f hat, the overall one, by a shrunken version of the tree that we just learned. And that is, in a way, the magic of AdaBoost and friends. If we would learn a tree and then a next tree that fixes its errors, and we really just sum these things, it can start to oscillate very badly. We don't want this, right? I mean, that's the one tree says, let's go left. You're like, no, we need to go right. And they don't really have to, they can't really balance each other out. So what we instead do is that the new f hat is going to be the old f hat plus lambda is the parameter that, or the coefficient that helps us to shrink, the new one. So the thing that we train, the f hat b, is already a weak learner, right? So it can't explain everything, but we even reduce its vote a little bit. Which value for lambda to choose, or how to choose it, cross-validation is your friend. Now, after we have done this, we have a new f hat, which means that we have new residuals. And with new residuals, then we can train the next f hat b, b plus 1. And we just keep on doing this until, well, we're either tired, satisfied, or maybe both. So boosting is really all built on learning slowly. And this is a pretty decent idea in statistical learning in general. Why? Why is it smart to learn things step by step just a little bit compared to, well, trying to explain the entire data in one go, which is essentially all the methods you've seen so far, what they try to do? Why? That's a pretty decent explanation. So you can think of, so if you very simplistically think of, okay, this, let's say, space of models, this is how much error we make, right? Then you would kind of hope that the error curve is convex, right? I mean, that's, and then what you were saying is not nonsense, but not necessary, because if we then make small enough steps, then we'll end up at the minimum, right? And that's absolutely fine. If we take giant steps, right, then, okay, we could bounce back and forth, right? But the methods we've seen, they're kind of protected against doing that. Now, the problem is, it's not so much that nature is against us, but often truth is stranger than fiction. So it doesn't just look like a nice convex shape. If it would be convex, then we can use all convex optimization, and we know exactly where the minimum is going to be without the whole bouncing thing. But actually, it's sort of like a 3D landscape in which we have all sorts of smaller and bigger dips, and we want to find, well, the lowest point, the lowest error. And by jumping too much around, by making too strong assumptions that the world is indeed just one big dip, we might actually miss the actual minimum. And taking smaller steps to essentially exploring the entire landscape, the lost landscape, one step at a time, gives us a higher chance of avoiding what would be local minima. It's essentially what it comes down to. One other way to think about it, in terms of bias and variance, if in one go we have to fit the ultimate model and all its parameters, well, if you just get some things a little bit wrong, you're screwed. Whereas if you do it a little bit at a time, one split, I mean, how difficult is it to learn one split, right? That is easy peasy. So there you are. You have lots of data to determine what is the right split, and we fix it time and time again. All is good. Okay. Yeah, number of trees. Use cross-validation. You need one way. Generally, well, as you can see here on the right-hand side, we have an example where it's, well, thousands of trees. Often, a few hundred is fine, right? I mean, that's in many cases 100 is absolutely fine. You can see that it drops very steeply, and then, well, do you really need this minimum, or is this one already fine, or that one fine? Often, depending on how similar the application domain is from your training data, there's not so much difference. Shrinkage, small. In a way, the smaller the better. Of course, the smaller you make it, the more trees you need to learn, so this goes a bit hand in hand. If you quickly want to have some decent results, use 0.01, something like that. Don't go above that, because then you get oscillating effects. Number of splits per tree, stick with stumps or very small trees. But of course, that also affects a little bit the training time. Good. Let's focus on the figures here. The left one, this one, is bagging. Over here we have boosting. And as you can see, the right one, I mean, the figure is not that great. I mean, that's, I should actually replot this, I think. But the linear decision boundary, I mean, trees don't like this, right? I mean, trees hate this linear decision boundaries. We discussed this last week. But boosting actually gets an overall much better approximation of this decision boundary than the left one. The left one really means that's just very large chunks that are just completely misclassified, right? So this shows that the fixing of your errors, this iterative fixing of your errors, I mean, this is quite powerful. Good. Now, very quickly, variable information, variable importance. Let's think back to one tree initially. And you may ask the question, how important is a particular variable, right? So if your domain expert gives you a data set with 1,000 variables, right, I mean that, and well, you can predict now something, this is great, but I mean, then they come to, okay, well, which attribute is now most important? Essentially what you can do, you can just say, okay, well, all attributes in the tree are important and the rest I don't care about. That's a bit too crude. You could say, okay, well, the ones that we make the splits on earliest, those are the most important, because that's why we chose them. But as like said, if you make a boo-boo at the beginning, right, I mean, you may need a lot of splits later to fix it. So it's not necessarily that the attributes that you use earlier are the bestest. Absolutely not. So how can you now interpret a tree with regard to which features are most important? Essentially what you can do, Leo Breiman, I mean, he's all over the place in this field. So for a single tree, essentially what you do, so big T is the tree, and we're going to look at the importance. So this is an I for importance, and it's going to look at the squared importance, and this is the L, and L is for the relevance of a predictor XL. Right? I mean, using a small I would have made sense, but then we have I subscript I, and that gets really weird. So this is the importance of variable L, predictor L for tree T. Essentially what we do, we simply walk over all the internal nodes of the tree, so basically every time we make a decision. Only if that node makes a decision on attribute L, we are interested in how much improvement in squared error do we get by using that particular split over just having the data that we have without that split. So we don't, so let's say if we look now at the leave, essentially what we're doing is we're comparing having a split on attribute L versus not having that split, just combining that data, right? And effectively we're doing, in a rough sense, the same also for other internal nodes, where we ignore that they're all split out. It's really like we either have this split into two parts or not at all, no split at all. This we all sum up, and that gives you the importance of an individual variable. For a single tree, this already helps a little bit if there's multiple splits on the same attribute, right? That's good. But this measure actually comes more, shines more, the moment you have a forest rather than just one tree, because one tree you can still look at, right, if the tree is not too large. But if you have a random forest or boosting with 1,000 trees, and your domain expert asks you, okay, well, which attribute is now the most important? Like, yeah, well, I don't know. This you can easily also compute over an entire forest, right? And nobody says that you have to just loop over the one tree. You can look over all the trees, and there you are. This is where the generalized version comes in, where, well, easy. Good. Just to give you an example, here for this is the hard data set. So here, Tal, or I think that my co-lecturer Krikamo would probably say, okay, Thai is most important, right? He's from Thailand, but I mean it's actually Tal. That's definitely the most important variable. That does not have to be the one that appears most. It's the one that really contributes most to the positive, let's say, decisions of this tree. Good. That's that with regard to trees. Trees decompose the space into regions and fit a constant model per each. You grow them greedily because it's NP hard as an optimization problem. They are, because of, well, amongst others, the greedy approach and the hard cuts, they're very brittle, right? High variance, low bias, right? Because you can make a cut anywhere in theory. And the more data you have, I mean, that's basically you can have infinitely many cuts if you like, if you have infinite data. Bagging, random forest, and boosting, well, I don't have to summarize because that I just said. Good. Clear? Are we done? Okay, then I want applause, and then we go to Ana Maria. I mean, if the email arrived. Unless there is an important question. Ben. So I gave the full anecdote last week. Essentially, every data science consultant who's worth their salt will first try a random forest. And if needs be, they will sell it as if it's like the newest of the greatest deep learning method and the most convolutional attention-based network. This is your first go-to method, because there's very few parameters, difficult parameters to set, and overall it will work well even for complicated target distributions. Will it necessarily be the best? No, but it sets a baseline that is already quite difficult to beat. Of course, if the shape of the data allows, then you can beat it with logistic regression, maybe with LDA, QDA, and so on and so forth. But overall, random forests, also boosting, you saw, works really well. Random forests are, in my book, slightly more preferable as the first method than boosting, because they're super easy to learn. They're super quick, right? And boosting, you have to do iteration by iteration by iteration, and we have to see. Out of bag sampling. This is what we also discussed in ClickEML, I think, covered this. If you have a data set of n samples, right, and we're now going to uniformly at random sample n data points from this with replacement, then on expectation, you will get roughly 2/3 of the points will be selected, right? So you have a number of duplicates, and there is a number of data points that don't get sampled into the bag sample. This we call the out of bag. And that we can use, amongst others, in a type of cross-validation also to evaluate then test errors. Yep. Say it again. Boosting depths. Boosted decision rules. Here, this one, you mean? Depth. The depth is of the tree. How many splits? So you have a split of a tree of just one split. That's the orange ochre color one. Depth 2 is you train on your each boosting sample a tree with where you allow 2 levels, a depth of 3. So basically you count the depth of a tree by the number of splits, the maximum number of splits from root to leaf. Yep. No, because then you would be getting close to overfitting. And this is the weird thing with boosting, is that it doesn't really want to do that. So it sort of stays away from 0, but it gets close to what it should. So this is one of those, well, I love this topic. Let's not talk about it, because then I don't have time for anything else. Yeah, good. Then let's quit this. Let's see if the email arrived. And if so, then... Yep. Yes. Oh, no, wait a second. Yeah, Anna Maria. Oh, right, that's you. Good. I don't know. I mean, if you don't know who you are, then it's enable editing slideshow. Slideshow from current slide. I'll share it on Zoom too. Where is Zoom? Zoom is here. Share. Zoom.
So, hello, and thank you for your attention. So my name is Anna Maria, and I'm from the chair of software engineering, and we are currently performing a study on program comprehension. So what is the study about? Here we analyze how a human brain reacts when it reads special code in Java. And like this, when you look at it, and then we see how whoop, like a light bulb goes on in your head, and we can see that something's happening. Well, not exactly like that, but that's how we imagine it. And what happens in the study? Basically, you go and you read and comprehend a bit of Java code, and then you answer some questions. And during the study, we then use EEG to measure your brain activation and an eye tracker to see what you're looking at. And this study, it lasts about 2 hours, including preparation. And what do you need to participate? You have to be enrolled in a master's program because we need a certain amount of programming expertise. You need to be able to deal with Java, and you need to be right-handed. Unfortunately, that's a viable criteria because the brain is structured uniquely for everyone. And for right-handed people, we can be sure that the speech processing part is on the left side of the brain. And for left-handed people, that is divided equally. And unfortunately, that means we need right-handed participants. Yes. So and now you're asking, why should I do this? What do I get out of it? Well, you will get some drinks and snacks from us. You will also get about 24 euros of compensation. So depending on how long the study lasts and how long we need to prepare. You also get a cool photo of yourself with an EEG on, which looks very interesting. So if anybody of you wants a cool photo of himself, just go to us. And you also get some experience with EEG and eye tracking, which I think is always fun to have. So if you want, you can just register by scanning the QR code, or well, I don't think anybody of you wants to type up this URL, so just you can just send a QR code. And if you have any more questions, you can just ask me now, or you can write me a mail. So are there any questions regarding the study? Yes? It can also be a while ago, so it's not, just important that you have some basic knowledge. No, but we have to set strict criteria, and then it's difficult to say yes to somebody else and no to somebody else, and explain this to somebody who is reviewing the study, because yeah, yes, and so no, so yeah, so it's unfortunate criteria because we had to draw the line somewhere. But anybody who is a master student, or who if you've got your certificate, if you just have submitted it and you've got your certificate, then you can come to me with that and show it. So I'm happy then to have you. So if anybody's interested, just scan the QR code, sign up. I'll also leave some flyers so that you can check or take them with you, depending on what you want. And yeah, I hope that I see some of you in the next few days or weeks for the study. And then thank you for the opportunity, and
Thank you.
on with the lecture.
Yeah, I will, always. Very good. Okay, so next part, support vector machines, which always in my head then reads like support the vector machines, but it's no, we will learn what we are supporting, or what these vectors are doing. Good. It's relatively hard cut from trees, right? This is I'm not necessarily saying the furthest possible away from trees, but don't forget anything about trees, but just park it in well, the left, the right side of your brain, whichever part you're currently not using so much. Before we can talk about support vector machines, I have to talk to you about hyperplanes. And I need some formulation, some definitions before we can really dive into the deep. What is a hyperplane? Well, in a 2D plot, it's a line. In a 3D plot, it's a plane. And well, that it remains a plane. That's why it's a hyperplane. P-dimensional vector space. In this figure, it's 2. It's a p-1 dimensional subspace. This is the formal definition, right? But if you picture it, just imagine a 3-dimensional space in which there is some plane. You can write this in multiple ways. Linear hyperplane, you can define essentially like a linear regression equation, but you have to set it to 0. And then these are the coefficients for how it, so there is no intercept for a hyperplane. Then an affine hyperplane that does have an intercept. So we same the same equation, we still set it to 0, and then well, beta naught is not 0. We're going to use this. We're going to both use plane hyperplanes and affine hyperplanes in the following. The most important thing, what we're going to be using is that a hyperplane cuts space in half. And what we can also have, and now let's see, so this is half space 1, this is half space 2. Vector beta 1 to beta p is the normal vector of the hyperplane. So in this particular case, the hyperplane can be seen as a 1 plus twice x1 plus thrice x2 equals to 0, otherwise not a hyperplane. That gives me the normal vector half times 2 and 3. Okay, good. Then we can also write this slightly different. We can normalize this vector. So we live in a unit space, which means I just take the 2, 3 and I divide it by the L2 norm of the 2 and 3. So basically I make sure that it fits in a unit ball. Okay, good. Now, the affine hyperplane, getting back to that, is what we have essentially here. So we have the hyperplane 1 plus x, twice x1, thrice x3. And if we set beta naught to 1, or if we just set f of x equals 1, then we arrive at this one over here, right? And that's, so basically we can shift the hyperplane up, respectively down, right? And this is going to be very useful because we will want to be able to determine if points are far away or close to our hyperplane. That's what we're going to be using, right? Good. This is then the fx minus 1, right? It's the opposite direction. Good. At one moment, we got feedback from one of you saying, okay, well, sometimes with the feeling that things are explained overly complicated. I think for the entire lecture, this is unfair and not true. ML is just simply about basics, and sometimes these are just naturally complicated. This slide, I can kind of see what you mean, right? I mean, that's, but we need this, we need this. We need to lay this groundwork, otherwise we can't do what we want to do. Because we're interested right now, not for the entire lecture, but for a large part in classification. And then you can ask yourself the question, can we classify using a hyperplane? And well, the answer is yes. In a way, you've already been doing so when we applied linear regression to do that. We could have called it hyperplane regression, but that would have perhaps been maximally confusing. So effectively, we have here, we have some data, we have some labels, there we are. Then we can assume a hyperplane, or actually no, a test vector is like a point that we want to test. Is it blue? Is it pink? Who knows, right? I mean, if we now build a classifier based on a separating hyperplane, we want to find a hyperplane that separates the two classes. This is the training data we have, right? So there exist infinitely many hyperplanes, basically every possible line that I can draw in this figure, right? Now, out of all of those, lots of them are pretty damn bad at separating the two classes, right? Here I have 3 examples of hyperplanes that separate the blues from the pinks. These are separating hyperplanes. How many separating hyperplanes are there? Not in this figure, but in this example. Somebody else than Ben. Infinite. Why? The answer was spot on. Spot on. So basically, we can choose any, but infinitesimally small, we can adjust, right? And so there's indeed infinitely many separating hyperplanes. So this leads to an interesting situation. Namely, there are either infinitely many or there are none. Did you say none? Good. Did you also want to say none or 0? Yeah, okay, good, good. It's neat. Either we have none, the data is not linearly separable, or we have, well, many, right? I mean, last week was between, infinitely many. So, good. Oops. So suppose that there exists one. That so we're first going to build it up, and then we're going to go to stuff that is not linearly separable. But, the hyperplane is defined by, well, that's the same definition as we had before, right? How do we now classify based on that? Just like with the linear regression classifier, based on the sign. So if something is on the positive side, what we also saw with the f equals 1, right? So if the beta naught has to be positive, that's what those, and these are all have a negative, hence those get the negative class. Can we extend this to multiple classes? Painfully, let's not think about it. The distance from a point to the hyperplane is informative about confidence in the classification. Why? Somebody give me the intuition. I'll allow Ben. Yes. Why? Because that is kind of reformulating what I have here. It's like a decision boundary, yes, yes. We'll see some let's say not counter examples, right? But in general, you're absolutely right. You're absolutely right. Good. Let's see. So, out of infinitely many hyperplanes, separating hyperplanes, right? If there exists one, there's infinitely many. We're interested in one. You don't want to just give a random separating hyperplane, right? What you're interested in is that hyperplane that maximizes the distance from the hyperplane to all the points. So for example, here, let me see, up. This is one example, right? I mean, that's a nice separating hyperplane. I can also adjust it like this. I'm going to flip-flop back and forth, right? I mean, the data remains, oops, the same, but one of those is better than the other. Oops. Which of those is better in your intuition? So this one or this one? This one? Why? If you flip back, then this distance over here, oops, this one over here and this one over here is less than in one step further. And that means for those 2 points, just those 2 points, right? I mean, it's a bit more of a coin flip. And we essentially want to, this is where the Bayesian decision boundary indeed comes in, we want to push them away as much as possible. So this has a lot to do also again with bias and variance, right? I mean, we want to avoid variance. This is what we do by choosing maximum margin. Now, the points closest to the hyperplane, these are those, they will all have the same vector, right? I mean, perhaps the sign is flipped, right? We try to make sure that these distances are all the same. That's the. These are these normal vectors, and we call them the support vectors, because if I give you that vector, then actually you know the hyperplane, right? So these are the things that I need, those vectors to define the hyperplane. In this particular case, 2-dimensional is quite easy. In a very high-dimensional one, in a complex data space, you might need many, as you can imagine. In general, only a small subset of all points, unless the data is, of course, very adversarially generated, right? How should the data look to get all data points as support vectors? One line? 2 lines? Okay, who bids more? 2 lines, you're absolutely right. That's basically perpendicular to each other, right? I mean, that's then the hyperplane would be exactly in the middle, and we need all of them, right? And that's in this definition. Effectively, if we just take 2, it would also be fine, but all of these points are now support vectors because they're exactly on the margin. Good. So the optimization problem is as follows. We want to maximize M. M is the margin, right? And that we want to maximize over all the coefficients. This M here does not make, so yeah, actually you also want to return that one, fine. We want to make sure that these the coefficients are normalized. It doesn't really matter, right? And that's but it allows us to uniquely identify one solution rather than we again have a whole bunch and like, okay, well, this one, we have this set of coefficients and we have another one where we just have a double and so on and so forth. Let's avoid that. That's what we do here. And then effectively, here we have something that looks very much like linear regression times the output needs to be larger than M. Let me take a sip. Finding the max margin classifier, we can just do this by convex optimization, because effectively there's a minimal margin, the maximal margin, and you can just step basically by tuning the line in the right direction, and there is only one minimum, right? You don't have the problem of what we were just discussing with the boosting, the flip-flopping and whatnot. So this is relatively straightforward. Yeah, okay, that we already discussed. Correct classification we discussed, or this is sufficiently clear. Here we have an example of a data set where there does not exist a separating hyperplane. That sucks. What are we to do? we can just give up. We can say, okay, let's just use random forests, boosting, whatnot, right? And that's, but we can also think a little bit harder about, okay, how can we make this idea of separating hyperplanes, max margin classifier, how can we now boost this up a little bit such that it is possible? How could we do this? There's no separating hyperplane. Yes, yes. Would you just mean, how would you do this? How would you ignore some of the points? Like, I don't like you, or that, do you have like a slightly more principled idea of? Almost. That's so you're really close to the margin. Should it be within or outside? I mean, elaborate a little bit more there. Within the margin, yes. Basically, if we now draw our favorite, what we would hope would be the separating hyperplane, and there's a few points that are close to it such that we don't have a max margin. If we now choose to ignore those, that we do have a large margin to all the rest of the points, that's pretty neat. Of course, how many points do you want to ignore? It can be a hyperparameter. I mean, that's, so we asked the domain experts to. Indeed. We're now coming to the support vector classifier, or the more loose classifier. Even if, okay, separating hyperplane may not be desirable. Exactly, so this is actually more the example that data set here we have separating hyperplane, great. Now with one data point, all of a sudden I flop the separating hyperplane extremely, well, it exists, but I think everybody will agree that something here in the middle is probably more desirable, right? Such that overall we have a hyperplane that is relatively far away from the decisions. So even if it exists, we don't always want it. So that is a point that you would like to ignore, right? And everybody else who raised their hands probably also wants to ignore that point or somehow don't take it into account so much. This is what we can do with the soft margin classifier. Okay, I think the title of these slides is then screwed up. Don't know how that happened. Definitely not my doing. Good. Yeah. Here we have an example hyperplane. And this is then essentially the margin we want. Like, look here, all these 3 points right on the margin, and that these are nice support vectors. This one is nicely far away. 8 and 1 are annoying, right? I mean, that's they're in the margin. We don't want them there, right? We would like to ignore them. It could also be, oops, that they are really on the wrong side of the hyperplane. So that's the example where we went, like, if there is no separating hyperplane, this is essentially what we want to ignore. In the other example, where they are too close for comfort, then we also want to ignore them. How can we do this? We change the optimization problem a little bit, such that we still maximize the margin. We still want to have a unit vector. That didn't change. We still want to make sure that all the classifications are correct, up till some error. And now, here, this epsilon, this is basically what we're now going to be using. We set a parameter C, which is the maximum budget of essentially points we want to ignore. And we're not going to count really the points, like 1 point, 2 point, 3 points, right? I mean, first of all, that would make the problem combinatorial and much more icky to optimize. No, we're actually just simply going to count. This is where the epsilons here come in. So it's a sum of all these epsilons. Epsilon is the distance from the hyperplane. And we only count for points that are within the margin. That's the error, basically, that we have, right? So if I give you a value of C is 0, what do we have? Yeah, also your answer? Exactly. If I give you a value C is infinite, because I'm a generous, well, not God, lecturer, generous lecturer. Infinite C. What are we going to get? Explosion. Completely natural phenomena. You can get anything, exactly. If that is explosion, yes, because that any hyperplane is now going to be fine, right? Basically, we can ignore any data point. So, and especially this is why I didn't choose C large, but really infinite. Even if the data set is infinitely large, we still have an explosion. That's good. Okay, so you want to set this margin, this allowed misclassifications, as a hyperparameter, and either we use cross-validation or we ask the domain expert, and then we see. Good. Yeah. Exactly. So one way to call this, these are the slack variables. So these are these distances, right? The points that are in the margin, and then we have a total budget. Yeah, okay. This is stuff that you can read. This is not so important. This slide we already discussed. The higher we set C, the more tolerant we become, right? I mean, or the other way around. I mean, the lower we set it, the less tolerant we become. And if we set it too large, then we have an explosion. I'll just walk through these slides just like that. As we also said already, I love it when I can just click through slides like that. So, yeah. With large C, we have a wide margin, many support vectors that we didn't say yet. So perhaps this is part of the explosion, right? If we put C into infinite, then all data points become a, well, then essentially nothing sensible happens. What is important though, this is why I like always pushing these examples to the extreme, because it helps to clarify the thinking a little bit. If we set the C value of C to 0, then we have a classifier that has a very high variance. Just one data point can flop things around quite massively, right? But low bias. The other one, so the higher C, then it starts to work the other way around. So low variance and potentially high bias, potentially, unless we really go to explosion mode. But, good. Okay, so yeah. Now you already know essentially all the necessary basics for, this is called then the support vector classifier, but we're this close to support vector machines. And maybe you have heard of support vector machines, SVMs for short. And SVMs were essentially, before deep learning blew onto the stage, right, after having been ignored for decades, SVMs, that they were really the shiznit. They were the key classifier, right? If you want to do cool stuff, then you use an SVM. Right? If you want to do stuff that works, random forest, but if you want to do theoretically cool stuff with guarantees, SVM, right? Essentially, we know all the basics already. Support vector machine, you could say, looks a lot like linear regression, logistic regression. It's just linear, right? It's just a hyperplane. And you're right, indeed. It's just a linear classifier. But of course, that sucks if the data is not, well, really linear, right? If it looks very, well, if it has like a circle, like a blob, right, with a circle around it, something like this, not linearly separable. This is very annoying. So yeah, that kind of sucks. So it took to somewhere in the 90s for people to realize, mid-90s specifically, how can we get around this? And all of you should, whether you right now on the spot can, that's a second, but should already be able to think of a solution to this. We have now a theoretically very nicely grounded linear classifier. But now we encounter a problem that's not linear. We've had this before. Logistic regression is also linear, but you know how to apply logistic regression to nonlinear problems. What is the trick? Same thing with linear regression. Purely linear regression. Polynomials. We change the basis function. That's let's say, the more general version of your answer, but both are correct. Which basis function should we change to? So you have a problem, right? In the sense of, if you have a problem in that, we have a classification problem, right? I mean, that's if you have a problem in general, then don't apply an SVM. But we have a classification problem. If we apply a plain linear classifier, you have really shitty results, right? And now, well, yes, we can use a set of basis functions. Which one should we do? Which one should we choose? This is a question we haven't really discussed so far in the course. Because indeed, the answer was polynomials, right? Or some other set of functions. Any idea? Yes? Why? Yes, yes. But effectively, this is what basis functions do, right? So the suggestion was, perhaps we should go to a higher dimensionality. But basis functions, in a way, do this. So the answer is correct. But in a way, basis functions and polynomials are all correct. Effectively, how you can think about it is that you can, let's take the example that I don't have it on a slide, right? And that's, so bear with me. But I have a nice blob of red points here, right? And that's in 2D. And I have a beautiful blue ring around it, right? And that's, yeah, linearly separable, my ass, right? No, there's a problem, right? But with a quite simple trick, namely quadratic distance, right? Polynomial kernel, we all of a sudden can separate the two. Effectively, adding a basis function, I say adding, right? So we still have x1, we still have x2, but in addition we have, well, x1 times x2, or we have x1 squared, x2 squared, whatever, right? Different basis functions. We're effectively expanding. If you think about the predictors as being 1 to p, we add additional dimensions, right? This is what you were saying. So we have these interaction functions, we called them earlier, right? And that's but you can think about it, if the data is a table, right, the original data for the p predictors, we add now a new column with x1 squared, and another new column for x2 squared, and a new column for x cubed. And if we keep that in mind, then what would be, in certain ways, the ultimate table? And in other ways, the most horrible table you can think of. How many basis functions would we like to add, to use? All of them, exactly. We should be greedy. All of them, yes, because God knows which one we need, right? Okay, well, there's of course a few practical problems, right? I mean, explosion, right? I mean, that's but also, okay, I mean, if you really have to calculate all of them, that is a bit problematic, right? But in theory, we want to use all of them. And then we have all sorts of overfitting problems, right? But this is the mindset where we would like to go. And that is what support vector machines allow us to do. Let's bring it down again. Let's keep it a bit more simple, and then I'll make the link to the infinities a bit later. So here we have a data set that looks a bit like the one I just hand waved, right? I mean, that's clearly non-linear. I mean, that's whether this is the best true boundary. I mean, yeah, well, actually probably it is, because it's completely arbitrary how and what. So no soft margin is going to help. We need, for example, oops, can't click in here, some quadratics, sure. We can add them. We still have the max margin classifier, or the soft margin classifier. We have the support vector classifier. Then all of a sudden starts to work. But then the question is, which ones do we add? There is one other problem that we have when we are going to add all possible basis functions, or even if we're not that greedy, a lot of them, right? Because not just that we have to find the coefficients, but effectively to classify with this beast, we need essentially the products, or the products of all the coefficients with the query point, because we need to know where it is, right? And we need to compare this to the hyperplane itself, right? Now, the more of these betas we have, the more computation steps we need. And if we now go to an infinitely sized table, so to speak, all possible basis functions, yeah, well, infinite it will take a bit long to compute, right? So we don't want to do this. We want to avoid that. This is where the kernel trick comes in. I'm going to just make sure that you know of it, right? If after this you don't fully understand it, I'm always going to say good. Because if you do fully understand it, then I want to know how and why, because this is not my intention to make you understand everything in fullest detail. For that, Krikkemold would happily give an entire course. He, together with his PhD advisor, a few others, they literally wrote the book on kernels and kernel machines, literally. So the idea is that we can rewrite the support vector classifier, especially the linear one, very easily as follows. So rather than having all these different betas, what we're going to have is we just have a beta naught, just an intercept, and then we have a sum over all the support vectors and then the inner product of those support vectors to the query point. And we weigh all those inner products with parameter alpha. This is what we do. And an inner product, that is easy peasy. That is computationally very easy. So, and alpha 1 are the parameters that we train. Oops, so, good. Because we only, so the alpha I is only for the support vectors, they're going to be non-zero. For all the others, they don't matter, right? They're beyond the margin, so it they don't contribute anything to the classification decision. So, now, the kernel trick you have here, this inner product, that is essentially the kernel trick. Now I'm going to jump right here, and then I'm going to jump back again. We can generalize that inner product to kernels in general. So kernel, like we discussed earlier in the course, essentially just a function that you apply that measures some distance between 2 points, right? And it has a number of other definitions on top of that. Quantify similarity between two data points. That's the key thing. Now, the linear kernel is just this plain inner product. And then you get, because it's linear, essentially you get Pearson correlation. But by reading it, not just like this, but essentially as a K kernel of X star and Xi, right? Then we can start to think about, okay, which other kernels allows us to have very efficient computation and at the same time allow us nonlinear decision boundaries. And that's where the kernel trick started to become really useful. For example, for the polynomial kernel, you have this definition. Hey, we again have inner products, very efficient to compute. We just need these alpha i's of just the support vectors, just compute this inner product, and there we are. The radial basis kernel, and for the polynomial, it's still up to degree d. So we have to choose d, right? And we could potentially push d all the way to infinity, but no. Now, the radial basis kernel is a bit special. Radial basis, essentially, you can think of it, it puts sort of like a Gaussian density around the training point. So if, let's say here I have a bunch of blue points, here I have a bunch of red points, right? Essentially, I put a little Gaussian density around all these data points, right? So if any query point gets close to an actual training point, it will have a high probability of getting the color, the class of that training point. That's how you can think of it. And we add all those densities up. So it's a bit like kernel density estimation. A radial basis is circular, right? I mean, for each of the individual training points. Now, one of the cool things, wait, that's not on this slide, but let me just going to say it immediately. The radial basis kernel, if you interpret it the right way, if you look at it the right way, gives us infinitely many dimensions. So it can essentially mimic anything. So we don't have to instantiate the actual infinitely wide table by using the RBF kernel. We can, especially if we have enough data, essentially approximate any shape, right? Approximate any shape, classify any shape, because it essentially works as if we have the infinite table with every possible basis function. Examples. Oh, this is for the linear one. This one is here for polynomial. Up. Now, the theorem I'm not going to show you, but for any kernel, subject to some definitions, there exists a function that just by taking 2 points in RP, so 2 data points, we get a similarity value, y. And essentially what we're now doing by applying a kernel, same thing as what we're doing by adding dimensions, by using polynomials as basis functions. If this is the true space that we're given, right? So basically this is the data that we're given, and here it's not linearly separable, right? By now adding the right, in this case, polynomial column, then under the right subspace, the data just looks like this. So there is a dimensionality, a subdimensionality, right? I mean, if we would have added the squared column here, in which, so this is P prime, in which it is linear separable. So again, the bridge to if we now have infinitely many columns, then there is always some subdimension psi for which things are linearly separable. And this is why for 10, 15 years, the sport du jour in machine learning land was to find kernels that are efficiently computable and have this infinite property. This infinite property is that you get, so up into space, are the reproducing kernel Hilbert space. This is a word that, well, just make sure that if you see it again, you're like, what is that, right? I mean, okay, it has something that would support vector machines. I'm not going to quiz you on what does it mean exactly, right? I mean, that's I'm not going to ask you to draw a reproducing kernel Hilbert space in the exam, right? That's no fear there, but know that it exists. Ben? Well, yeah, yes. No, so the importance, so that's for any kernel, there is a function over which we can do the inner product, right? That's the first step. But then you want to do you also want to have this infinity property. Because the linear kernel, right, the one that we started off with, right, I mean, that's just a plain inner product, is also a kernel. That's essentially, let's say, the one base case here, which the linear kernel is clearly not infinite, right? I mean, that it is perfect if the problem is linearly separable, but if not, then it kind of sucks. So that is the main point here. So the importance of this theorem is really that there is a mapping between kernels and these functions, right? And or basically that you can rewrite it as an inner product. So the moment you have a kernel, you can write it as an inner product, you have efficiency. And now the question is more, which kernels are now better to use than others? And this is where we go into this infinity land, and then you're in a reproducing kernel Hilbert space. Yes. Exactly. So for the linear kernel, we're in a very low dimensional space, right? It doesn't blow it up. Which is essentially what I'm trying to also, I mean, for those that think a bit more visually, with this infinitely sized table, right? I mean, let's go back to my example, the blob with the ring around it. If you now add the right feature, essentially what you get now a three-dimensional space where the ring lives here and the blob lives here. That allows me to cut it, right? So what you now need is for your problem, your classification problem, to have a kernel that separates things. And this is where now a linear kernel or some other restrictive kernel, polynomial kernel, right? It may work very well. And if you give a polynomial kernel of high enough degree, then, well, it may work for many cases, but not necessarily for all. If you now have these special kernels that can really go to an infinitely sized space, there we are, right? Then you have a very powerful kernel. RBF does that by putting these small blobs around each data point. I can also think a bit about it, because if I now crank the data points up to infinity, then, and I just classify things from close to a data point of a training point as being the same class, this allows me to classify any arbitrary shape. Right? The decision boundary can really can be the most complicated, its own tail-eating dragon, right? That is what RBF can do. Of course, if you don't have enough data, then RBF kind of sucks. Oh, mind you, so this is kind of the example I just gave. So if you now have the blob in the middle, a ring around it, under the right projection, in this case polynomial, then all of a sudden it becomes linearly separable. There's the top part and the bottom part. Here's the RBF kernel. Let's focus on the example on the right, where we currently have the linear kernel, right? And that's now by drawing essentially a small Gaussian or a small circle of influence around every training point, you get this as the decision boundary. So these here, the densities that each of those data points give, let's say the probability of being red in this particular case, or magenta, that gives you a space in which the probability of red is higher than the probability of blue. This is how you can think about it. This is what the RBF kernel effectively does. So you have a very non-linearly drawn decision boundary, And well, this is the peak of this blue part, there's a peak of this blue part, this is the peak of this magenta part, and this is then the decision boundary. Good. So for a very long time, if you wanted to classify, and you did not like trees or forests for whatever reason, support vector machine with an RBF kernel. That was the state of the art for a very long time. And I'm not going to argue against it, but my preference is more on trees. Good. Let's see. Time flies when you're having fun. I mean, I totally forgot that we were also supposed to have a break. Let me give a, actually, let's just take a 10-minute break. And then I wrap up, because the key parts that we really want to digest I now covered. And then afterwards, I want to discuss a little bit, okay, how do things hang together? What are the advantages, disadvantages? So let's sink it in. If there's any questions, can either take them right now or after the break. And I think after the break might be better. So if you have a question, don't forget it. And if you don't have a question yet, try to think of one. Let's reconvene in 10 minutes. So. Yeah. So let's get started again. I think I said let's have a break for 10 minutes, roughly 10 minutes ago, right? And then I was chatting, I forgot the time, so good. Yeah. Support vector machine. By using a kernel, you now have the choice of a kernel. And therewith, I mean, you're not just stuck with a linear, like a purely linear classifier, right? And that you can lift it into a higher dimensional space. Some people call this the lifting trick. This is not a formal term, right? But essentially, this padding your table with these virtual columns, and then perhaps even infinitely many, you lift it into a higher dimensional space. In this higher dimensional space, there will exist, if you added the right features, your linear separating hyperplane. That's all good. The kernel trick allows you to efficiently, or at least much more efficiently, because SVMs are still computationally a nightmare, but much more efficiently compute, well, both at runtime, the distances, but specifically to learn, because you can just do inner products. That's the kernel trick. Yeah. SVMs have been expanded to all sorts of data types, because in the end, yeah, you just need the right kernel. You just need a kernel that can tell, okay, it does this molecule, how similar is it to that molecule, right? And perhaps, well, the linear match is not really going to work, right, unless you can serialize and have some edit distance. But the moment that you know that something looks graph structured, then you come up with a graph kernel. And there is decades of work on graph kernels, I mean, based on random walks, whatnot. If you have a string, a genetic string, or some other, I mean, that's a piece of text, how do you compare those? For that, you can define an arbitrary similarity function that may or may not be a kernel. Kernel needs to be positive, semi-definite, and a few other things. Doesn't really matter right now, but essentially define a kernel that fits your data type. Boom, you can apply an SVM and everything is good, right? Whereas, for example, with a decision tree or random forest, if your data now consists of graphs, what are you going to split on exactly, right? I mean, what is the feature space on which you can split? Maybe difficult to envision. You can't really use similarities. So hence, they both have their advantages, these classes. And you have a question? In theory, no. Because the more dimensions, the merrier. Because that gives you just more options to find the linearly separating hyperplane. Of course, the tricky part is that if I have very few samples and I use a very powerful kernel, this is not exactly the same, but almost the same as using, let's say, linear regression with very, very many basis functions, which means that we have to fit many, many parameters. And yeah, that is tricky. And here you think perhaps, okay, wait a second, but this kernel trick avoids us doing all these parameters. Yeah, but you still have to measure all these similarities. And if you have very few data points, but you're measuring similarities in a very high dimensional space, estimating this similarities becomes very difficult. So effectively, you want to have many data points. Otherwise, it doesn't make so much sense. At the same time, the more data points you have, you also have to now compute these values alpha for all of these data points. Only for those that are not support vectors, it will go to 0. But initially, I mean, you have, well, essentially a randomly chosen hyperplane, right? And they're all non-zero. So this means that if you have infinite many data points, SVMs are horrible. Kernel trick or not, right? While you're optimizing, when you get the hyperplane closer and closer to where it should be, then things start to become good. Unless we go back to the example that we went to in the beginning, right? I mean, if we have these two lines completely parallel to each other, then all of them will remain support vectors. So yeah, there's really two sides to the story. Good. Yeah, kernel trick, and essentially applying. So the kernel trick is partially. I mean, people overload it, right? Kernel trick is primarily that you just use a kernel function to determine similarities and then compute these through an inner product in some way. The kernel trick often is used more as like, well, let's apply a kernel to my data to explode it into a very high dimensional space in which it may be easier to obtain what I want, right? So in the higher dimensional space, you could also say this the right space in which you can solve the problem. You can apply it to many different things. I mean, density estimation, already mentioned. LDA, PCA, you can plug it in. Kernelized PCA is definitely a thing. Kernelized rich regression is one of the most powerful regression techniques that we know. If you use the right kernel, then you can fit essentially any function with any problem, if you have enough data and enough patience. Good. Let's continue. Just to show how things work and how it now relates to things that you already know. So heart disease data that we've been looking at multiple times, 13 predictors, binary target, well, not so many training points, but fair. And we're going to compare LDA to linear SVM. This is quite fair because, well, LDA is obviously linear, right? And that, remember LDA, right? To essentially fit the Gaussian, same densities, and we have a linear decision boundary. And the linear SVM, well, this is effectively what we had with the support vector classifier, right? I mean that there's no real support vector machine magic going, no kernel magic going on there. Now, the right-hand side, we have a plot what you normally compute also the AUC, the area under the curve with. But we have if we order the points by essentially how accurate we are. So on the y-axis, or the x-axis, sorry, we have the false positive rate. So how often do we say that it's class plus when it's not? And on the y-axis, we have the true positive rate. So the ideal classifier, where is it? Or where would it be in this plot? Top left corner. Yep. That would live right here. Because then we have, or well, actually here, because if it's this top left corner, then we have an accuracy above 100%, and then, well, I doubt your math, but okay, that's my bad. Indeed. So then we have 100% accuracy. Everything is true positive, and well, we have 0 false positive, right? Effectively, we don't always have this. So if we now we order our decisions based on well, either a confidence, distance to the margin, right? We order them in one way or the other. And then we have a certain threshold that we can set. And for each of those thresholds, we essentially have a new classifier, right? Essentially how you can interpret it. That's what these curves are. So that's the receiver operand curve. So for the one where we don't make any decision at all, yeah, then of course we don't do anything well. And then if for those that we make, so basically if the distance has to be infinite from the decision plane, for example, for an SVM. And then we shrink this, and at one moment, poof, you can see that those that we are very far away from the decision plane, or the ones where we're most confident, there we make very few errors, but it's good. It's good, right? And then at one moment it starts to taper off. Each of those points on this curve, for both LDA and the SVM, are individual classifiers. So an ROC analysis helps you to identify for your particular setup, what is the best classifier you want to put to practice. Sometimes you don't really care if now and then it makes a mistake by saying plus when it's minus, right? And sometimes you really care. Healthcare applications, for example, right? I mean, that's do you want somebody into an unnecessary but very in very highly involved surgery, right? I mean, that's or do you rather do a few additional tests, stuff like this. And sometimes when the tests or whatever the treatment is very cheap, okay, well then a few false positives, not so bad, right? So what you can see here is that the support vector machine with the linear kernel, so the support vector classifier and LDA, well, they're not exactly the same, but they're essentially the same, right? And these curves, this is not a coincidence. This is not a coincidence. Okay, slightly different data set. I mean, it outperforms it. Effectively, SVM is and remains a linear classifier. So it just depends on what kernel you use. Well, here, it's purely linear, so it's the same. Here we use a different kernel, proper SVM, slight difference. So it's really what extra information can this kernel, can the similarities that it identifies, can we tease out of the data? So SVM, you could say, is the grown-up version of LDA and QDA. Let's compare it slightly differently. Okay, wait. different order than I expected. Let's actually go to the one that I do expect here. Effectively, especially for the radial basis kernel, I've been talking about drawing a small Gaussian, right? Some Gaussian density around the point, right? I mean well, that gets both close to what we're doing with LDA, but also what we're doing with logistic regression. Because in logistic regression, what we're essentially trying to guesstimate is what is the probability for a given point. This is where the point lives, right? This is the probability for being red. This is the probability for being blue. And if it's, you have the Bayesian decision boundary. If it's the probability for being red is higher than blue, then we say red, and vice versa, right? I mean, but it's all about estimating these probability densities. This is what logistic regression does, right? Now, in the radial basis function specifically, we're also drawing these Gaussians or something very similar to it, and you can essentially interpret it as such. And then we add a linear classifier on top of it. So if you do the math, and we're not going to do it, rest assured, but they are almost the same. Not exactly, but they're almost the same. And this is what you see also in this slide. So we can also make it a bit more apparent by, so essentially what it comes down to, let's first look at this. So here we have the loss for SVM, respectively logistic regression. This is for different parameters. As you can see, it follows a very similar curve. For the logistic regression, it's nice and curvy. And SVM, it sort of goes straight down, and then where does this come from? So this is the key difference between the two, right? And that, because they estimate densities, draw a line, and it's just mean how do they now regularize? The optimization problem for the SVM, if you rewrite it, is essentially what is now the distance from the true value and the predicted value to 1. So you take the maximum, set now the positive for the negative side of the hyperplane, and we regularize based on the coefficients. It's effectively what we do. And we have some weighting term. For logistic regression, or if you actually now rewrite it to regularized regression, same thing. We have some likelihood term. This is what we try to fit in logistic regression. And then we have some laws based on the penalty. Now, in SVM, we just have this sum, so straight. And for logistic regression, this is slightly smoother. It's the only key difference. So the name of this, so the one, so for logistic, you can call it as ridge regression, whatever. I mean, so basically you have a ridge penalty. It looks a bit like this. But effectively for SVMs, we call it the hinge loss. If you estimate your probabilities well enough, so in a, what's the word? Non-parametric way, or you are lucky enough to choose the distribution the right way, and you plug that well-estimated distribution into logistic regression, it's going to do as well as SVM will do with the proper kernel, right? Or if you have enough data points with the RBF kernel, that's all fine. It's going to be basically exactly the same. Do we have, I really, yeah, where's my slide? They're going to perform on par. Now let's go back here. So we have different parameters for essentially in this RBF kernel for how far do we spread things out. I'm going to wrap up in a second. So we have different variants. So these are basically how far do we spread things out, how do we integrate things. It's a hyperparameter. And for 10 to the -1 in this particular case, we get very close to this ultimate thing. Actually, for this data set, and especially the distances between this data set, so how sparse is it in the data space that we originally have, that is the optimal way of spreading out the probability mass. So that is effectively what the weighing parameter, right? So the shrinkage parameter in this case affects. So it's a hyperparameter that you need to play with. And if you, well, just like with any hyperparameter, sometimes it's best, sometimes it's worst. You need to optimize it. Good. This I'm going to skip because that is really a bit over the top. Nobody's going to ask me. All of this is grayed out, so it's not going to be part of the exam, right? But, Mind you, pluses does not necessarily mean it's not going to be part of the exam. Pluses mean ESL book, right? But if it's grayed out, then, and I try to choose a shade of gray that is sufficiently readable, but also still identifiable as gray, right? That's, can we extend SVMs to multi-class? Yes. Do you need to know how? No. Hence gray. But if you want to know, this is how we do it. Can we extend, this should also be gray, support vector machines to regression? Yes. But it's a bit more difficult to explain this really properly, right? So for many of the topics in EML, we really chose consciously to start from regression and then afterwards do a classification. For support vector machines, classification is really the easier approach. The way you can think about it, that's what I'm going to give you. I'm going to give you the intuition. So here we have a regression data set. All the x's are the data points. And we want to find, well, we basically want to have some curve through it, right? I mean, that's, or the linear line curve through it. Essentially, we want to now find that curve that grabs as many possible points as close to the curve as possible, right? While keeping the margin around this curve the same. So with a linear kernel, this would be this line, and this would be the margin, right? But rather than having the points as far away as the margin, you kind of want to have them in the margin, right? Because then they really support your regression line. Effectively, what you're trying to do in support vector regression, you're trying to find within the kernel that you have sort of you can sort of like a tunnel through your data that is as smooth as possible. This is where the parameters come in. As smooth as possible, that captures as many data points as possible. And let's say the wire that goes inside of this tube, that is essentially your regression line. This is how you can envision it. Just like here, this is also essentially a tunnel, right? A tube. Now in two-dimensional space, so, and we just look at it from the side. Okay. More tubes. What we have, let me see, do I want to? Actually, no. This is also going to be grayed out. It's time. But, because we're not going to ask questions about support vector regression in the exam. You have my word. And it's just important that you know that it exists, but how it works. If you really are dying to know, next semester, machine learning core lecture, undoubtedly going to have a lot more detail about kernel machines. For now, key idea. We have some data and we are trying to find a hyperplane. And ideally a separating hyperplane, but it doesn't always exist. So we want to have a hyperplane that is maximally distant to the training points. But it doesn't always exist, so sometimes they are on the wrong side. This is why we have a budget. And we go from the separating hyperplane to a max margin classifier to the support vector classifier. That's the one where we have some budget with the slack variables. And if we now don't do this plainly on the data, but we look at the data to the lens of a kernel by projecting it into this infinitely dimensional space, or whatever the kernel does, that we can actually create a space in which the problem is linearly separable. If you use the wrong kernel, sucks to be you, right? I mean, that sucks to be your client if somebody is paying for your services. If you apply the right kernel, there you are. Everything is fine. The only data points that are in the end really of interest are the support vectors that together define the hyperplane in that high dimensional space, right? So if we apply a kernel, they don't form a hyperplane in the original space, but in the, good. Let's see, yeah. The kernel trick is used for two different ways. The one is let's apply a function to then do our business in a high dimensional space because that makes certain things easier, right? That's the wrong way how to use it, but people do it nevertheless. Effectively, it means that rather than computing difficult stuff, we just do an inner product. That's what it comes down to. Linear SVM is essentially logistic regression. And in many cases, logistic regression, so if you choose your densities wisely, will perform, if the stars are aligned well for you, very similar to an SVM. It's effectively what I have to say today. And given that I caught up on trees and we had some intermission, and we had a break. I'm actually quite proud that we're only 12 minutes over time. Are there any questions? No? Then thank you very much for your attention. See you again next week. Bye-bye.